Hello, everyone. My name is Yifang Ban. I'm the PI for the EU AI for Global Change project. On behalf of my team, I would like to tell you about our research on Earth observation big data and AI for global environmental change monitoring. According to the IPCC report in 2021, now we have code red for humanity. Climate change is widespread and we're at a tipping point from retreating of the ice caps, glacier, to melting of sea ice, to droughts, uh, wildfires, and urban flooding. Uh, our planet faces grand challenges. In recent years, wildfire has increased in frequency, intensity, and duration, has devastating consequences. Urbanization is another grand challenge. We're expecting 2.5 billion urban dwellers moving to urban areas by 2050. Nearly 90% of this increase will be in Asia and Africa, where there's a lack of timely and reliable data to support sustainable planning. Even though urban area occupies less than 2% of global land area, it consumes nearly 80% of the energy and produce 70% of the pollution, and resulting in urban heat island, urban flooding, severe bad air quality, and also affect biodiversity. So here's the example of urbanization. Dubai was transformed from a small desert town to a mega city. And cities around the world would like to have a digital twin to support their planning decisions, not only a static one, but also a dynamic one. That means whatever has changed in the built-up areas, they wanted to know and incorporate that. The planners wanted to know and incorporate that into their planning decision making. Since the launch of Landsat in 1972, many Earth observation satellites have been launched. They provide huge volume of data for environmental change monitoring at a global scale. So here is the Sentinel satellite, Sentinel-1, Sentinel-1, and Sentinel-2 can provide global coverage every 5 to 6 days. These data are open and free, really a great opportunity for developing applications and data products to support real-time monitoring or near real-time change detection. So these Earth observation big data present opportunities for near real-time monitoring of phenomena affecting built and natural environment. The dense time series can be used for analysis of global environmental changes and provide new possibility for operational and reliable services. However, there are some challenges as well. We need innovative computing infrastructure to handle, store, and process data, need new methods and algorithms to extract valuable information. We also need to integrate analysis of the satellite images together with other geospatial big data, for example, data from ground sensors, crowdsourced data, as well as from social media. The overall objectives of this research is to develop innovative and globally applicable methods for global environmental change monitoring using EO big data and deep learning, focusing on urbanization and wildfires monitoring at the current phase, in the future, we will be moving on to other urgent environmental change monitoring. Uh, so we expect to support sustainable urban planning and support City of Stockholm's challenges on digitalization and climate change resilience, UN habitats monitoring of SDG 11 indicators, uh, support timely and reliable wildfire emergency response, and sustainable forest management and climate resilience. So we can contribute to SDG goals 11, 13, and 15, support smart city development, as well as the Sendai framework for disaster reduction, and also Paris Agreement. So we have an interdisciplinary team, myself and Andrea from Division of Geoinformatics, from ADE School, and Josephine and Hossein are from Computer Vision and Machine Learning EES School, Ula from Environmental Science side, also from ADE School. We also have a variety of end users and stakeholders from local city level and regional authorities of Stockholm, UN Habitat, and the wildfire side, Swedish Civil Contingency Agency, Forest Agency, British Columbia Wildfire Services, and the Ministry of Forest. So here's some examples of satellite data we've been using. The Sentinel-2 data, beautiful images when they're cloud-free. However, when you have cloud, there's a need of other type of data. For example, radar data here, it can penetrate through cloud smoke and also the image at night. So very reliable data source. For using supervised deep learning, we need to use training labels. So we leverage existing data set, for example, the Microsoft building footprints in US and Canada, and some cities in Uganda and Tanzania to train a model and then deploy it in other cities around the world. But this has challenges, I will tell in a little bit. For urban change label, we use SpaceNet 7 data sets over 60 different cities around the world. And here are some examples of this continuous change detection data set. And the methodology we developed is so-called dual stream architecture for multimodal data. We have radar, we have optical data. We use those both for mapping and change detection. So the dual stream approach proved to be effective. And using machine learning, deep learning, and using Sentinel-1, Sentinel-2 data, where Sentinel-2 on the left, Sentinel-1 on the right, we're able to extract build-up areas anywhere around the world from different time, and you can see the urbanization trend. This is example in Beijing, using the urban extraction result. And as I mentioned earlier, the deep learning training labels are from North America and some cities in a couple of countries in Africa, but urban comes in different forms, height, density. We need the trend model using the only North American data do not perform as well. So we have developed the unsupervised domain adaptation approach that have been proven really effective. This paper was published this summer in Remote Sensing of the Environment. So if you're interested, you can check it out. And some examples of our result performed really well in Stockholm in both high density and low density build-up areas. And here's just result from Beijing. It performed similarly well. And Dar es Salaam, our results outperformed the state-of-the-art products. For urban change detection, again, these are the training data sets we used, the SpaceNet 7 and OSCD. We also collect our own validation labels to validate the result. So the methods we developed, as mentioned earlier, dual stream unit using Siamese network and also using domain adaptation. And here are just some change detection results. Continuous change detection were performed in Stockholm, in Beijing, and in Shanghai. The results are quite good. And also in the SpaceNet 7 sites, our results are very close to the ground truth. And we also assess environmental impact as well. So I don't have time to discuss that. If you're interested, check out our papers. And I'd like to mention urban land cover change affect the urban thermal environment. So here is the land cover corresponding to urban heat island. And so it's really important to monitor this to support resilient cities. So we also developed an app for land use efficiency monitoring. That's a SDG indicator. Try out our lab app if you're interested. For wildfire monitoring, we have on the left a variety of satellite images at low resolution. You can really see active fires every few minutes to twice daily. Then to these images, maybe every few days. However, as we said earlier, optical data have the clouds, therefore radar images are quite useful, or use all images available in order to track and detect fires. And so we have, in order to achieve high resolution daily image, we have used a machine learning data fusion approach generated a very high resolution image that can be used for daily monitoring. And we also did field work to collect validation samples to support our methodology development. So we have developed methods, deep learning based methods for early detection of active fires, and also near real-time monitoring of wildfires, how they progress over time. So here are the examples of the progression result in Elephant Hill. We're able to track them as soon as there's a new image. And here's the example in Australia, near Melbourne. We were able to detect a fire on the first days. If we have, provide such information and the fire being put out, using this information, then this fire wouldn't have expanded to uncontrollable, and it became almost 1 million hectares burned and damaged to vegetation, biodiversity, and property. And so another example of radar-based monitoring of fire progression in Fraser Island bushfire, and compare our products with the low resolution product, 20 meter, you have much detailed information. And we developed three wildfire apps for British Columbia, for California, and for EU. You are welcome to try KTH Wildfire Monitor. And that's all. Thank you very much for your attention.